Hey guys, just a short update video with a few new features for the BMS, but also some fixes of things that have been going on. The first one is the set clock stretch limit, which I'd mentioned in previous videos. I wasn't able to get any communication going without the change of the set clock stretch limit. Even after putting the correct pull-ups on, it was still giving me issues. So I've got it on the screen here, and what I had to do last time was move this down here. Not sure why doing it after the wire again helped, but what I did have to do initially was set this to 1500. It worked. It was still a little bit intermittent, a bit twitchy. What I did find was that if I set that to 2000, it worked fantastic. But it was still curious why it was doing this. So looking in this, chatting with a few people, and also mentioned it to Stuart, the clever gentleman who designed this board and code. And that was when kind of something became apparent, and he mentioned about the speed of the AT Tiny 85s. From the factory, they come at 1 megahertz, and Stuart's code had wanted them set at 8 megahertz. Now that's where the discrepancy came into play. So by setting the stretch limit at 2000, it's kind of masking the issue, but didn't get rid of all the issues in my view. It was still sometimes a bit finicky about the order in which you did things and how you set them up. But once I'd set the speed and the other fuses to the right way and set the set clock stretch limit, sorry, it's hard to pronounce, back to 1000, that just worked perfect straight out. So that's where that is set back. I've changed that in my code now, so I'm back with the default as it should be. That worked well for Stuart, and thankfully it's now working well for myself. So the way to do that is you need to set the fuses on the board. Now this is where, like, hands up, I didn't even notice this, and Stuart had put this in his code for the module. I did these modules a little while ago, and all the excitement of getting them working, and just set the firmware, and then off it went with the code. Stuart had put this in, and I didn't see it. It was kind of also my belief that the settings which he's got up here, I did take note of, and I made sure that these were set, and you would do that via tools and then these relevant settings here. But the issue is that just setting them here isn't enough. That's not going to actually set the fuses on the board. So what you need to do is set these correctly, and to be honest, everything is set correctly except the LTO. So it's a case of going in there and setting that to enabled, which I've already done there. And then you can either do it in two. Well, the first way I'm going to do it is you can do it via the IDE, which I think is the far easier way. So this is why I've kind of got the webcam going at the moment. What I've got is a BSP ASP cable here. I've just got this hooked up to a USB extension cable. And then you get your module. The pin 1 is the red wire there, which has the MISO SAK and reset on this side. And then if we plug that in there, you can see the green lights come on, the board's getting power, and that's working. So what we need to do is go back into tools, change the programmer from a AVR ISP to a USB ASP. As I mentioned, everything else is set, and then I'm going to do a burn bootloader. It's going to go through, and then you will get some errors potentially about the set SAK frequency. That's just a warning, that's fine. And as you can see, it's done burning the bootloader. So what we're going to need to do now is, with everything still set, we're just going to program the board with a code. And that should compile a sketch and then push that out of the board. It is set so that it should leave the EEPROM alone, but seems that setting the bootloader will erase it. So if you've been through this process already, and like I'd provisioned all 7 boards, you're going to have to provision them again basically. Now, as I alluded in the earlier videos, I had to drop into the test program that Stuart had written to be able to provision them, because you seem to get a bit more feedback. But I found that now the set clock rate is correct with these fuses being correct. That wasn't needed, and I was able to go through. All you've got to do is be patient and wait till the green light comes on, and then you know that it's good to provision. So that's that board with the correct bootloader and the code set. And if I go, can plug them into there to either port, and then excuse the mess, but I've just basically jury rigged up 7 cells so I can test the board in the house, which is far easier, because that's one of the issues I found, is dropping in and out of the house. It's sometimes a pain. So you notice it flashed there initially, and now we've got a solid green light, and the solid green light indicates that it's set to factory defaults and it needs provisioned. So what I can do is drop into the interface, and we'll go to modules once this comes back up. Sometimes just take a second. There you go, to draw the graphs. So we've already got the other modules provisioned, 6 of them. If we click on, I'll tell you what I'll do, I'll set this to the left hand side of the screen, and we're going to put the output here. And if I reset him there by hitting the reset button, the Wii mouse, we can see we've got the output, basically the serial output. So if I close that, go back in, just need the modules to appear. I've just reset the board there, so sometimes it takes a couple of seconds just to find everything. Even though you can see them in the list here for the modules. Normally comes up much quicker than this, but this is because I'm doing it on the video. Obviously it's going to be a pain. Tell you what, close that. I'll try a refresh of the page. Now what you've got to do is make sure that you don't do the provision until you can see all the modules listed here. Even though you can see them here, you need everything to be correct before you do that. The danger is that it'll provision it with the first module ID 24, and then you'll have 2 modules with the same ID on the I2C bus, which is not good. Let's try that one more time. Okay, so you can see that it's rebooted. Connect, that's the IP we're on. If we go back to that, we can do a refresh. Let's see those. There you go. Okay, so you do get the odd little thing like that. So as we saw there, we've got 24 to 29, so the first 6 modules. We're going to do provision. Click OK, and you can see there the dialog stays on the screen, but it's instantaneously provisioned, and it's found module number 30, which is basically just assigning the next number. So then if we close that, if you give it a second, then the 7th module should appear, and we should hopefully be getting some data. Okay, so we've got a bit of a flashing light party going on. That's finding all the modules again. Okay, and there you go, and we've got module 30. So what I'm going to do is I'm just going to get my multimeter. We'll go through the recalibration of this module. So where's the camera? There we go. The question is, yeah. Okay. So what I have found is that initially you generally would put the actual voltage reading in this box here. For some reason I've found that initially if you try and put something in here, it's not updating here, and you'll see there it's got set voltage calibration 0.0, and that's not the case. So we can just put a fake figure in there, and if we do that, it's set at 4.0 volts. So then what we'll do is the module that we've just added, which is this guy here. I'm just going to try and do this upside down. And you'll see that that voltage is a freshly charged cell, so that's 4.157. So if I put in 4.157, click OK, and then it automatically works out what the voltage calibration figure should be. And you can see there it's assigned it. And then in a second, there you go, 4.157. So we've got that correct calibration. That module is going to write it to the EEPROM, and everything's in there. By default as well, we need to just set this to 1.0 for the temperature, which is something I'm going to come to now. You'll notice now that these figures are a lot lower, and that's and also a floating point with some decimal places, and that's because they are Celsius. So that's something that I have changed now in the code, which I will switch back to. Yeah, and we go to across to the first thing I've changed is the what I've changed is the temperature value in the structure for the cell module was set to a 16-bit unsigned integer. I could possibly go through and back figure where Stuart is modified that, but the problem is I found for the calculations for the Steinhart configuration calculations for the thermistor were all done a floating point. So rather than do a lot of conversion back and forth and such like, I've basically changed that there to be a float instead of an unsigned 16-bit integer. So once I've done that, in the main BMS controller module, what you will notice is there's a whole lot more variables defined, and this is it's a 10k thermistor that we're using. The voltage is 3.3 volts, and the resistor that's set is a 20k resistor to go in line with the thermistor. If you're using a different value, you can update that there, and that will amend the calculations accordingly. What you will need to do is, if you're using a different thermistor on the 10k one, you'll need to look at the data sheet, and you'll need to get these corresponding values. And these are the 0 volt and the, well, you can pick in any arbitrary amount if you want, but then just put that relevant amount in there. Say for 50 volt, 50 Celsius, but you'll put those in there. So that's in there, and then I've created a function which is temp convert. Now this is not as pretty as Stuart's code, I must confess. I did consider doing a separate file, but it's such a small piece of code I didn't think that was really necessary. So what we have, just to start, is the thermistor setup, and this is using the Steinhart calculation method for the thermistor. So this is the calculates beta, and then the RINF, and then it then runs through the calculation based on the figures that you've put in, and then it will return the temperature in Celsius in the form of a float. And where I'm basically calling that, as soon as it's read in the initial cell module quick check, is there. So previously where it was just read from the board, and that was read as a 16-bit unsigned integer, at the moment now I'm just reading that straight into a float, and it converts it straight away, and that's stored in the cell module, and then we can do whatever we want with it. And that was a relatively easy change for this part. The hard part was just amending some of the maths. Now I did get the majority of that, I shall confess, from this gentleman that wrote an instructable. The only difference being that it was pull up versus pull down, and so the temperature would actually be inverted, and so I had to amend the formula for that, which I have done for the temp convert, and that was a multiply instead of a divide. So I've amended that correctly so the temperature goes the correct way. And then the other side of things that I needed to amend was in the loader.js file here, and that was just to amend the scaling. So I've set it from 100 degrees Celsius to minus 25 degrees. That can be amended, and feel free to fork it and change those files if you wish. But for me, that should be more than sufficient. And as you can see there, it's reading correctly. It's about, no, actually, rather than guess, I can see it's about 22 degrees in the room. There is going to be slight variances, and these boards are all here quite close together, so they should be identical, but there'll be a slight variance in the resistance on the thermistor and also on the inline resistor for the divider. You could technically measure those, but the thing is, because it's one function to cover all the modules, it's kind of just a bit of an average, so you're never going to get super accurate. I don't say that's a huge issue, because when we're putting these in, what we're basically looking for is huge temperature curves. So if your battery pack is starting to go thermonuclear and you want to cut things off, that's what you want to detect. We're not looking for tiny variances in 1 or 2 degrees really. That's by the by, and you'll notice that they're all down to about 22 there. So what you'll see is that you'll get those fluctuating up and down ever so slightly, but that's not something I'm concerned about. The other change I've went and done is, since the temperature monitoring was in there, what I wanted to do was be able to pull this into Grafana. So what I've done is I've went and I've overhauled a little bit, not hugely, although it did take me a while, I must confess, is the InfluxDB and where it posts these now. The change I've made as well is that it's now posting it is, each time it posts the values of the 7 modules, it's posting the voltage, the temperature, and also the bypass status. It's posting those all in one go, so they're going to all get an identical timestamp. And with InfluxDB being a time-based database, that's going to work much better. It wasn't a huge issue because they were always within under a second easily. It was microseconds, but it just looks nicer in the code when they get an identical timestamp, and that works out nicer. So basically what we're doing is we're stepping through the array of each of the modules. It's checking if the values is set to true, to say that they're valid values, sorry. I had missed an equal sign. It was late at night when I was doing it last time, so the check wasn't actually being done correctly, but that's working correctly now. So even though it's reading pretty well and accurate and reliably, if it did get an erroneous reading of, say, 50 volts or something silly like that, it's not going to post that into the InfluxDB now, and it'll just only post what's relevant. And basically it steps through and just builds up this array, and does a separate one per line. So as part of that, we've had to change the structure of how it's doing it with InfluxDB. So we've got a top level field there of cells. Underneath that you've got a cell and then the cell number, so you'll have cell 1. Then it posts the voltage is equal to whatever the voltage is for cell 1, the temperature for cell 1, and what the bypass status is for cell 1. Then it'll go through to the next one, cell 2, and the voltage for cell 2 and such like. And it builds that up in a string field, and then it's just going to post that in one go, and that's been working great and working reliable. I must confess, I'm not a guru on InfluxDB, so it took me a little while to get that working correctly, but you know, it's working pretty well, and I'm happy with that now. So to that end, I've been modifying my code for the interface, I should say, for Grafana. So now we've got the 6 cells, and that's because I've only just provisioned the 7th cell, so that's not going to appear there. I'll show you how we do that. But as also, we've got the cell voltages, which is fantastic. So I've had this running a little while. Admittedly, it's a bit juxtaposed because we have all this data from outside and for the power pack and for how that's going, the overall voltage. This is currently reading the internal setup. But it doesn't matter if it's in reading the internal test cells or whether it's reading outside. It's still going to work just the same. Obviously, just these values don't match up to there. But it's been working great. Reading everything fine. Yeah, so can't complain on that front. I've got 6 cells in here, 6 cells in here, and the addition now of the temperature. So what we can do is, I don't know which cell this is, but if I put my finger on there, I'll turn my multimeter off, and that should heat that up. Now it reads it every minute, so as long as I keep this up, the pressure, and then it should heat that cell up. And there you go. That's just coincidental. So orange, that's cell 4, that's up to 31 degrees. So actually if I just change that back to there, today so far, it takes a little while. You can see the swirly pattern there. It's updating the graphs. I'll go through, and actually if I let go of that, once it finally goes through, there you go, so that one's updated, and there you go. So you can see that spike, and then we should see that drop down also. The bypass status has been posted, but I'm not seeing any values coming through as yet that are different from 0. So it should just be a boolean, so it should be 0 or 1. But I need to go back and double check, and because that just would be nice to see. Ideally, it would be nice to see it change the color here from blue to red if that cell's on bypass. So I need to look into, because with the data being posted, I just need to look into how I can code that in. Maybe it needs a different plugin for Grafana. I've been looking at a few this lunchtime, so there might be one that can do what we need. But yeah, as you can see there, it's spiked up, and then it should hopefully come back down. Temperature will change pretty quickly. So on the whole, that's kind of getting what we want. You know, we've got the voltages. It's tracking over time, but I like having it just at a glance view. You'll notice these are out of whack completely because these are just individual cells. So these are going to have different capacities. So there is a certain parasitic draw from these. Stuart's done an excellent job, and that is pretty low. But there is still going to be a draw nonetheless. You know, it's running some circuitry. So because these are different values, they initially started off at about 4.2 volts fully charged. But they've declined differently, and that's how you're seeing the different voltages here. The temperatures there, you'll notice that's went back down to 23 volts. So you can see the difference down there. I'll just very quickly run through here, and what we'll see is that we have, where is it? We've got 1, 2, 3, 4, 5. So that should be 5. And he should be 6. They're being a bit muddled up. But what we will do is, so this is cell 6. So if I update that correctly, so I think in my haste I've labelled them up slightly wrong. 1, 2, 3, 4. That's millimeters. 1, 2, 3, 4, 5, 6, 7. No, apologise, I already had 7 there. So I've just confused myself. That's 2, 3, 4, 5, 6, and this should be 7. And what we're going to do is we're going to see where, now this is the old structure that was cell voltages, so we need to remove that second filter, and that allows you to change the first filter. So we're going to change that to cells, where cell is equal to 7. We're going to go for the field value voltage. We're going to go for the last one in the alias, so it looks okay. It's going to be cell 7. So we can do that there. Yep, and go back to the dashboard, and there you go, we've got cell 7, and that's showing 4.15 volts. If we go back into the screen here, it just takes a second to redraw the graphs, and that'll give you the buttons back, and then we can click on, it's 4.14 there, it's changed slightly since we went in. Yeah, 4.144, and it's just, one of them's rounded down, one's rounded up. Yeah, so it's there or thereabouts, but for the accuracy I need, that's perfect. So the next steps I'm going to be able to
work on the bypass status as I mentioned and possibly get them to roll into here. But on the whole, everything's working correctly. Last thing I did have, nope, I've mentioned that already, the minus 25 to 100 degrees in the file. So yeah, so that's pretty much everything all done. And then the next step is going to be the bypass status and then the actual balancing, which I'm going to start looking at as well, but I believe Stuart is working on, and doubtless Stuart's will be far quicker and far more efficient. But that's it, guys. So I hope you enjoyed it. I hope it's helping some people along, and I hope people are doing it. So feel free to comment below if you're working on this and if it's been useful. If you've got any input, by all means let us know. So feel free to subscribe, share. Cheers guys, bye.